Hello! In part 1 and part 2 we talked about some principal LED circuit designs. Today we will talk how to calculate the pre-resistor and the parallel resistor in the LED circuits. Additionally, I have some further information about the leakage resistance, which I forgot to mention in part 2. See you after the intro. First, some addition to part 2. In part 2 I mentioned with an open switch there is some leakage current around the switch caused by dirt and dust. But there is also a leakage current of the transistor or the driver IC. These leakage currents differ from part to part. This small bipolar junction transistor has a leakage current from 0.015 microamp to 5 microamp. This field effect transistor has a leakage current from 1 to 10 microamps, and this driver IC has a leakage current from 50 to 500 microamps. And all have in common that with the increasing temperature the leakage current will increase. All the following calculations are based on a leakage resistance. If only the leakage current is available, calculate the maximum voltage on the open switch divided by the leakage current and you will get the equivalent leakage resistance. Now we want to calculate the pre-resistor R. We have a supply voltage U with 12 volt, a voltage drop across the switching transistor US from 0.2 volt, of LED forward voltage ULED of 3.2 volt, a tolerance of the LED forward voltage of plus minus 0.1 volt, and the desired LED current is 10 milliamp. First we calculate the voltage drop UR. It's the supply voltage minus the forward voltage on the LED minus the voltage drop on the switching transistor. UR is U minus ULED minus US with concrete numbers 12 volt minus 3.2 volt minus 0.2 volt. UR is 8.6 volt. With Ohm's law we calculate the resistance R. R is UR divided by ILED with concrete numbers 8.6 volt divided by 10 milliamp. The pre-resistance R is 860 ohm. We select the standard resistor R is 866 ohm. The power dissipation of the resistance R is the voltage multiplied with the current. Power is ILED times UR with concrete numbers 10 milliamp times 8.6 volt is 86 milliwatt, so we select a standard resistor with 100 milliwatt. The brightness tolerance of an indicator background illumination has different sources, e.g. the brightness tolerance of the LED, the resistance tolerance of the pre-resistor R, the tolerance of the supply voltage, the tolerance of the voltage drop on the switching transistor, and the forward voltage tolerance of the LED. I want now to calculate the brightness tolerance, which is caused by the LED forward voltage tolerance. The brightness of a LED is pretty close a linear function of the current through the LED. So the tolerance of the brightness is the delta of the LED current divided by the absolute LED current. The change of the LED current is caused by the change of the LED voltage divided by the resistance, and the absolute current is the voltage at the resistor divided by the resistor. Now we bring both parts here on the main fraction line, and we can then remove the R and get delta brightness is delta ULED divided by UR. With concrete numbers, we get plus minus 0.1 volt divided by 8.6 volt is plus minus 0.0116, which result in a brightness tolerance caused by the LED forward voltage of plus minus 1.16%. In this circuit, we want to calculate the pre-resistor R and the parallel resistor RP. We have a supply voltage U of 5 volt, a voltage drop on the switching transistor US of 0.2 volt, a LED forward voltage of 2.1 volt, a desired LED off voltage of 1.0 volt, a LED forward voltage tolerance of plus minus 0.1 volt, a desired LED current of 2 mA, and the leakage resistance RL is 100 kilo ohm. First we want to calculate RP. RP has the purpose in case the LED is switched off and we have a leakage resistance RL of 100 kilo ohm, that the voltage drop on the LED is limited to 1 volt. To make the calculation easier, we assume that the leakage resistance RL is much bigger than the resistance R of the pre-resistor. Much bigger means leakage resistance RL is at least 10 times R. In this case we can ignore R. So we get this simplified circuit. We have a supply voltage U with a serial connection of RP and RL. At RP we have a voltage drop of U LED off and the remaining voltage drop is U RL. Now we get the following ratio. U divided by U LED off is the same like RL plus RP divided by RP, like here. We can now separate to RL divided by RP plus RP divided by RP, and this term is 1. RL divided by RP plus 1. Now we bring the plus 1 with minus on the other side and get U divided by U LED off minus 1 is RL divided by RP, and we get U minus U LED off divided by U LED off is RL divided by RP. Now we bring RP with multiplication to this side and this term inverted to the other side and get RP is RL times U LED off divided by U minus U LED off. With concrete numbers, 100 kilo ohm times 1 volt divided by 5 volt minus 1 volt. The resistance of RP is 25 kilo ohm. Now we have to select a resistor with 25 kilo ohm or less. The next standard resistor has a resistance of 24.9 kilo ohm. Now let us assume that in another part of the circuit is already a 22 kilo ohm resistor. In this case we will select 22 kilo ohm to reduce the part complexity and the cost of the circuit. Now we want to calculate the maximum power dissipation on the resistor. This is the case when the LED is switched on and we have the forward voltage on the resistor. We calculate U LED times U LED divided by RP with concrete numbers 2.1 volt times 2.1 volt divided by 22 kilo ohm. This gives the maximum power dissipation of 0.2 milliwatt. Now we calculate the resistance of the pre-resistor R for the parallel circuit of the LED and the parallel resistor RP. The resistance of the parallel resistor RP is 22 kilo ohm. The voltage UR is the supply voltage U minus the forward voltage U LED minus the voltage drop on the switching transistor. UR is U minus ULED minus US with concrete numbers 5 volt minus 2.1 volt minus 0.2 volt. UR is 2.7 volt. The current I through the resistor is the current IRP through the parallel resistor plus the current ILED through the LED. The current IRP is the forward voltage ULED divided by the resistance RP. With concrete numbers, I is 2.1 volt divided by 22 kilo ohm plus 2 milliamp is 0.095 milliamp plus 2 milliamp. I is 2.095 milliamp. Now we calculate R as UR divided by I with concrete numbers 2.7 volt divided by 2.095 milliamp. R is 1289 ohm and we select the standard resistor 1.3 kilo ohm. Now we check our original assumption that RL is much bigger than R. And we see 100 kilo ohm is much bigger than 1.3 kilo ohm, so the assumption was okay. The power of the pre-resistor R is UR times UR divided by R with concrete numbers 2.7 volt times 2.7 volt divided by 1.3 kilo ohm. So the power dissipation in the pre-resistor is 5.6 milliwatt. Also here we want to calculate the brightness tolerance caused by the LED forward voltage tolerance. The brightness tolerance is delta ILED divided by ILED is delta ULED divided by R divided by UR divided by R. We bring now both to the main fraction bar and get delta ULED times R divided by R times UR. Now we can remove R and get the brightness tolerance is delta ULED divided by UR. With concrete numbers, plus minus 0.1 volt divided by 2.7 volt is plus minus 0.037 is a brightness tolerance of plus minus 3.7% caused by the forward voltage tolerance. Exercise 1. We have a supply voltage U of 12 volt. We have a voltage drop on the switching transistor of 0.3 volt. We have on each LED a forward voltage drop of 3 volt. And the tolerance of the forward voltage is plus minus 0.1 volt and the current through the LED should be set to 15 milliamp. Calculate the voltage drop UR, the resistance R, the power dissipation in the resistor R and the brightness tolerance caused by the LED forward voltage tolerance. Press the pause button and do the math yourself. The voltage drop UR is the supply voltage U minus 3 times the forward voltage of the LED minus the voltage drop on the switching transistor. UR is U minus 3 times ULED minus US with concrete numbers 12 volt minus 3 times 3 volt minus 0.3 volt. UR is 2.7 volt. With Ohm's law we get R is UR divided by ILED with concrete numbers 2.7 volt divided by 15 milliamp. R is 180 ohm and we select the standard resistor 180 ohm. Finally we calculate the power dissipation in the resistor R is ILED times UR with concrete numbers 15 milliamp times 2.7 volt. The power dissipation in the resistor is 41 milliwatt, so we select a 50 milliwatt type. The brightness tolerance is delta ILED divided by ILED is delta ULED times 3 divided by R divided by UR divided by R. We bring both to the main fraction bar and get delta U LED times 3 times R divided by R times UR. Now we remove R and get the brightness tolerance is delta U LED times 3 divided by UR. With concrete numbers we get plus minus 0.1 volt times 3 divided by 2.7 volt is plus minus 0.111 is a brightness tolerance of plus minus 11.1% caused by the forward voltage tolerance of the LED. Exercise 2. The supply voltage U is 24 volt. The voltage drop on the switching transistor is 0.5 volt. The forward voltage of each LED is 2.5 volt. The off voltage of the LED should be set to 1 volt. The tolerance of the forward voltage is plus minus 0.1 volt. The current through the LEDs should be set to 25 milliamp and the leakage resistance RL is 100 kilo ohm. Calculate the voltage drop UR, the resistance R, the resistance RP, the power dissipation of the two resistors, and the brightness tolerance caused by the forward voltage tolerance. Press the pause button and do the math yourself. First we calculate the resistance RP set with the open switching transistor and a leakage resistance of RL 100 kilo ohm. We get a ULED off voltage drop of 1 volt. With the assumption that the leakage resistance RL is much bigger than the resistance R, we can ignore R and simplify the circuit. We have a supply voltage U and a serial connection of RP and RL. Now the ratio U divided by U LED off is the same as RL plus RP divided by RP. Now we separate this to RL divided by RP plus RP divided by RP is RL divided by RP plus 1. Now we bring the plus 1 with minus to the other side and we get U minus ULED off divided by ULED off is RL divided by RP. Now we bring RP with multiplication to this side and this term inverted to the other side and get RP is RL times ULED off divided by U minus ULED off. With concrete numbers, RP is 100 kilo ohm times 1 volt divided by 24 volt minus 1 volt. RP is 4347 ohm, so we select the standard resistor with 4.3 kilo ohm. The power dissipation in the resistor RP is 2 times ULED to the power of 2 divided by RP is 2 times 2.5 volt to the power of 2 divided by 4.3 kilo ohm. The power dissipation in the resistor RP is 5.8 milliwatt. To calculate the resistance R, we need the voltage drop UR and the current I. The voltage drop UR is the supply voltage U minus 2 times the forward voltage ULED minus the voltage drop on the switching transistor US. UR is U minus 2 times ULED minus US with concrete numbers 24 volt minus 2 times 2.5 volt minus 0.5 volt. The voltage drop UR is 18.5 volt. The current I through the resistor R is the current IRP through the resistor RP plus the current ILED through the LEDs. The current IRP is 2 times ULED divided by the resistance RP. So we get I is 2 times ULED divided by RP plus ILED with concrete numbers. 2 times 2.5 volt divided by 4.3 kilo ohm plus 25 milliamp is 1.2 milliamp plus 25 milliamp. I is 26.2 milliamp. With Ohm's law we get R is UR divided by I. With concrete numbers 18.5 volt divided by 26.2 milliamp. R is 706 ohm, so we select 715 ohm standard resistor. Now the check of our assumption that RL is much bigger than R. 100 kilo ohm is much bigger than 750 ohm, so our assumption is okay. Now we calculate the power dissipation of the resistor R. It's UR times UR divided by R. With concrete numbers 18.5 volt times 18.5 volt divided by 715 ohm. The power dissipation in the resistor R is 479 milliwatt, so we select a 0.5 watt type. The brightness tolerance is delta I LED divided by I LED is delta ULED times 2 divided by R divided by UR divided by R. We bring the two terms to the main fraction bar and get delta ULED times 2 times R divided by R times UR. We can remove R and get the brightness tolerance is delta ULED times 2 divided by UR. With concrete numbers, plus minus 0.1 volt times 2 divided by 18.5 volt is plus minus 0.0108 is a brightness tolerance of plus minus 1.08% caused by the ULED forward voltage tolerance. Some final remarks. Think about the power of the resistors. Especially the pre-resistors have often a power dissipation of several hundred milliwatts, and you must ensure that this power is guided in a proper way to the ambient. We have also seen the lower the voltage drop across the pre-resistor, the more the forward voltage tolerance of the LEDs affects the brightness. If you like to minimize the brightness tolerance caused by the forward voltage tolerance of the LEDs or the variation of the supply voltage, you should think about controlling the LED with current sources. Here 2 links to current sources. That's all for today. If you like my video, give me a thumbs up and subscribe my channel. And to be informed about new videos, activate the bell. Bye bye.